everybody, welcome to my presentation of the paper Scheduling of a Large-Scale Industrial Make and Pack Process with Finite Intermediate Buffer using Discrete-time and Precedence-based Models. My name is Klanke. I'm a research assistant at the TU Dortmund University Process Dynamics and Operations Group, and this work was done in collaboration with Mr. Yfantis, formerly also at TU Dortmund, Mr. Corominas from Procter & Gamble, and Professor Sebastian Engell, head of the Process Dynamics and Operations Group. I would like to start my talk by introducing the EU project CoPro. In this project, we dealt with integrated scheduling and control problems, coordination of coupled plant operation in highly integrated chemical production sites, and also finding efficient model formulations for a variety of process systems engineering problems. The project will end in June 2020. And one of the case studies we dealt with in this project is the following production plant. This is a production plant run by the company Procter & Gamble to produce consumer goods. It has two stages, a formulation and a packing stage. And on the left you see the coupled layout. On the right you see the decoupled layout. The coupled layout is the current layout, operated in this way. And the optimization and scheduling of this coupled layout has been dealt with by Mr. Yfantis and his colleagues from the third research group in Greece. And in this work, we're going to focus on the decoupled layout mainly. Now, why to choose such a decoupled layout? In this case, for some products, the formulation stage runs much faster than the packing stage, and for other products, it's the other way around. So we can waive to have a synchronization between stages through the decoupling via a buffer. And so for fast production in the formulation stage, the buffer can be filled and product can be withdrawn by the packing stage. Now for fast formulation stage, the operation finishes earlier. Packing stage can still withdraw products from the buffer, and the formulation stage can already start producing other products, which might then be redirected to the buffer or to other packing stages. This yields maximal utilization of the available processing rates and an overall increase in productivity. This is enhanced by the decoupling of changeovers. When a changeover takes place in the formulation unit here, then the packing unit can operate at this point in time by withdrawing products from the buffer. This would not be possible in the coupled layout. A smaller investment is required compared to adding more production lines, at least this is expected. And the disadvantages are clearly that this varying bottleneck behavior with the additional decisions included by the buffer increases the complexity of the scheduling task at hand. And this is why an optimization-based solution is sought. To formalize the scheduling problem more, the task at hand is to allocate a set of orders I to a set of lines J, sequencing those operations and maximizing throughput as a result. For the process characteristics of that plant are that we have fixed processing times, so no decisions involved. We have product families, so a few intermediates map to a high number of final products. This is due to the fact that the final products might have differ only in printing or in the type of package, but contain the same intermediate. Constraints which have to be imposed are the sequence-dependent changeover times have to be considered. Eligibility constraints on the packing lines are there simply because the variety of packed products necessitates mechanical operations where you need specialized packing units. The buffer capacity constraints have to be satisfied. We're not allowed to overfill the buffer. And finally, deadlines or on the finishing times of final products are imposed. Previously, a discrete time model has been developed, also in the DYN group, which takes as main decisions the variables W, I, J, T. When they are 1, an operation starts, and the buffer is continuously filled throughout this time, simply because the plant operates continuously, And when the corresponding packing operation is started, then the buffer level is depleted again by that operation. The buffer balance is not as easy as displayed here, because there's an aggregation over different product families. The buffer is storing product families or intermediates and not final products. The problem has been tried to be solved by a monolithic approach, so setting up the model and solving it in one step, but that's computationally not tractable, partly due to the fine resolution in the time grid, and therefore a decomposition approach has been developed, which takes subsets ik from the set of all orders I in every iteration k. These subsets are scheduled, partial schedules result, and in the next iteration then the new model is instantiated or initialized with the previous solution. The time horizon is shifted, and the schedules are therefore concatenated until we receive a complete solution, and these subproblems are computationally tractable in contrast to the monolithic approach. This approach has been originally developed by Mr. Yfantis, the reference you can find here, but it has or bears some disadvantages which we tackle in this work. Amongst the problems is the fact that there's a limited look ahead because the set of orders scheduled in every iteration is quite small, and so one aim would be to increase the look ahead to more operations. We do not have explicit sequencing information in the discrete-time model, so it's not possible to optimize changeovers directly, although there's some optimization potential left. And finally, it's not desirable to extend the discrete-time model formulation in any way because even the submodels are quite large already. The approach in this work is to use an immediate precedence-based model to give an optimized allocation sequence on a subset of all processing lines. This immediate precedence-based model is much smaller, solves faster than the discrete-time model, and therefore we can increase the look-ahead horizon in every iteration. We neglect the buffer balance in the immediate precedence-based model. We also only apply this to a subset of all packing lines. With it, use the solution and the sequence it yields to reduce the degrees of freedom in the discrete-time model, which will then also solve faster and do not have to, has to take less decisions. The overview of the approach is given here. All problem specifications and the subset of orders ik press is given to the precedence-based model. As already mentioned, this set is larger than the set of orders scheduled in the discrete-time model. The precedence-based model then yields a sequence on all the presorted lines. The presorted lines are only a subset of all packing lines. This is because the discrete-time model will be much more constrained due to the sequences enforced in it by the solution of the precedence-based model. And the solution quality might even deteriorate if too many degrees of freedom are taken away in the discrete-time model. These results are finally then given into the second step, the order heuristic. Its task is to decide for the subset of orders ik to be scheduled in the discrete-time model. Finally, by enforcing allocation and sequence constraints on the presorted lines in the discrete-time model, we yield or obtain the timing of all the individual products of one iteration. These results are then fed back into the precedence-based model, so including completion times. It is then in the next iteration initialized with the current state of the schedule. The properties of the precedence-based model include that we have decision variables x, I prime j, which are 1 if a product I is conducted, or the processing of product I is conducted prior to processing product I prime. Usually a changeover time has to elapse in between. And therefore we can sum up the total changeover times in this model and include them in the objective function formulation. So the second term is the penalization of total changeover times. The first term is a normalized make span, and this normalization has to be done due to the fact that we shift the time horizons in the decomposition approach, and this has to be compensated. As already mentioned, the set of products in the precedence-based model is larger than in the discrete-time model, so we have advantages with respect to the look ahead within the decomposition, and the solution times even decrease. The task of the second step, the audit heuristic, is to decide for a set of operations to be scheduled in the discrete-time model, partly from the set of operations scheduled in the precedence-based model, and partly from the initial order list. Because the precedence-based model only operates on a subset of all lines, we of course also need to choose products here in IK which do not run on the set of lines JPress. What criteria is the audit heuristic deciding for? For one, the deadlines are considered, and secondly, load balancing. The deadlines are accounted for by checking if all orders in a sequence on a pre-sorted line have the same deadline, and if not, the product with the smallest deadline will have to go in the set IK, because we cannot be sure to meet the deadlines with the given sequences from the precedence-based model, because the timings will maybe shift afterwards in the discrete time model, and thus the model might become infeasible. The load balancing is done mostly for products which do not run on the pre-sorted lines JPress, and products on these lines are chosen to be as equally distributed amongst all of these lines, obtain a decent balanced utilization of the lines. And the result from the precedence-based model in terms of allocation and sequence are enforced via constraints in the discrete time model, with fixed allocation of products by setting them equal to the allocation which has been determined by the precedence-based model, and this is the variable yij is the optimal solution of the allocation variables in the precedence-based model. In a similar manner, we fix the sequences of products on JPress. This is done by enforcing that the finishing time of a product being produced prior to another is also smaller than the starting time of the subsequent product in the discrete time model. Finally, the buffer balance feasibility has to be guaranteed by the discrete time model as well. So this is done by shifting operations on the set of pre-sorted lines JPress, and still the discrete time model can choose allocation and timing of all operations in the formulation lines J1 and in all non-pre-sorted lines. The algorithm workflow is as follows. This small example takes a set of 6 operations in the set of orders of the precedence-based model. We neglect the formulation lines J1 here and only have a look at the pre-sorted lines and the non-pre-sorted lines here. The gray bars here indicate that the decisions of the previous iterations have already been fixed, so we cannot change timing and allocation of these gray products here. The precedence-based model then solves for an optimal sequence and allocation on the pre-sorted lines. Then the audit heuristic chooses which products go into the set of orders IK, partly based on the products here, so products from the pre-sorted lines, but also it takes products which go on the non-pre-sorted lines. The discrete time model finally sets the timing of the operation, so you see the green operation, its timing was shifted, and of course for all other products it's fixed as well. Finally, the decisions are fixed for the next operation, for the next iteration, and the new models are initialized with this state of the schedule. A result of this algorithm looks as follows. This example contained scheduling 6 operations per iteration in the discrete time model and 15 operations per iteration in the precedence-based model. A total of 91 products were scheduled. we can see 12 production units. The upper 6 are formulation units. The bottom 6 are packing lines. Every distinct color here corresponds to a unique final packed product. The numbers above the bars indicate the number of the product family. The black bars indicate changeovers. At the top here, the 6 lines only have blue colored products, simply because the distinctive features of those operations is the product family or the intermediate type only, and not the type of final product. We can see that we have to introduce only very small idle times on the packing lines, which is definitely a sign of a high quality schedule for this case study. We have a decent load balancing in the formulation lines. This is not the case for the packing lines, but this is mainly due to the eligibility constraints imposed on the packing lines. All in all, the schedule quality is very satisfying. In numbers, which we can see in this table, we compared applying the discrete-time model only, so no pre-optimization, to what if we include the precedence-based model in the decomposition approach as well. In terms of make, span, completion time, and changeover, only medium improvements have been made. But most importantly, the idle times could be reduced significantly. The computation time also decrease, although we include an additional model to be solved. But since the precedence-based model solves quite quickly compared to the discrete-time model, and we introduce additional constraints on the discrete-time model, this computational time reduction is reasonable. I'd like to sum up my talk. We extended the existing discrete-time model and the decomposition approach with a precedence-based presorting, able to directly optimize changeovers. It is all of this was integrated into the existing decomposition approach. We conclude that the significant reductions in idle time could be observed, not only for the problem instance which you've seen in the previous slide, but also for all other instances this approach has been tested on. We don't incur additional computational costs. Finally, this approach has been integrated into the Procter & Gamble IT and OT environment of that plant to automate the scheduling even more. With that, I would like to thank you very much for your interest. The results of this publication has been funded by the EU's Horizon 2020 program, and for that I'd like to thank you as well. I'd like to close my talk by saying goodbye.